We're going. We're live. Yay.
Yes, we are live.
Hello, everybody.
Hello.
And welcome to the CMS Experiment Control Room.
Hi, we are glad to welcome you to the compact muon solenoid experiment. We are here in the control room and we will be showing you the CMS detector today.
Yeah, the CMS detector is the most beautiful of all four of the four main detectors.
That's an objective statement.
Very objective.
Yeah.
No bias there at all.
You want that?
Nah, not right now. You're gonna see exactly why we have this opinion. Andres is gonna take you almost 100 meters underground to visit the actual detector itself.
Yeah.
So do you want to introduce yourself?
Yeah, so my name is Andres. I grew up in Puerto Rico and I've been working in CMS for quite a few years. And yeah, I'm a physicist. I work with a lot of detectors and operating and fixing the detectors and so on.
My name is Claire. I grew up in South Africa. I moved to CERN and I spent my first part of my life on the Atlas experiment. And then I moved to CMS in 2022. So yeah, we are going to have a good time today. Why don't you guys, people who are viewing us on YouTube, if you want to write down where you're from, that would be great. We can see who we're talking to around the world. And of course, if you have any questions, anything you'd like to know about CMS, about CERN, about particle physics, or about something that you're going to be seeing today, feel free to write that in the YouTube chat, and we will do our best to answer it.
Cool. I'm gonna get going and start heading downstairs, but I'll be listening in and I'll jump in every now and then.
Okay, cool. Yeah, so I'm going to stay with you up here in the control room while Andres gets kitted up in his helmet and safety boots, and get ready to go downstairs. Let's talk a little bit about what is this experiment and where we are. So we are one of the four large experiments at the Large Hadron Collider in CERN. So right now we are in a little town called Cessy in France. And on the screen over there, you can see where it says CMS right on the left-hand side of your page. That's an overview of the French Swiss Valley. You can see the Alps. There's Mont Blanc in the background. There's Lake Geneva. You can get an idea of the scale of the ring of the LHC by the airport, which is in the middle there. And that yellow ring shows where the Large Hadron Collider is 100 meters underground. So the Large Hadron Collider is the world's most powerful particle detector. And we take protons and we speed these protons up to very, very close to the speed of light. So we give them a huge amount of energy. We have protons going in two ways around the detector at the same time. And then at 4 points around the ring, the accelerator people adjust the beams and bring them in so that those protons actually collide each other billions of times per second. And I've been saying protons because most of the time that's what we do collide inside the LHC. We just hit a major milestone. In fact, this past week, we finished the last ever proton-proton collisions inside the LHC. There will be no more proton-proton collisions inside the LHC but we will be upgrading the LHC in the future. Andres is going underground or getting ready to go underground. Do you want to say what you're doing there?
Yes. So just very quickly, I can just mention that we are going through the personnel access device, and this grants us access to the underground areas. And so part of the process is you scan your dosimeter, which is your personal dosimeter, which is this guy. And then after the system acknowledges that you have all the correct access to go underground, it will then basically take a picture of your iris and compare that to the database to make sure that the person going in is actually the person who has the right to go downstairs. So we're gonna now go in the elevator and we're gonna lose the connection for a little bit. So this might be a good moment to answer some questions if there's any already, but we will give the floor back to you.
We do, we do. We have a question from YouTube. Derek asked, why do we collide protons and not another type of particle? Actually, we don't only collide protons. So we just finished the proton run, but right now we're getting ready. We're preparing for 3 weeks of running where we're going to be colliding lead ions together. And this is very cool because it's a completely different type of physics between smashing protons and smashing lead together. It can teach us many different things about the way that the universe works. So, for example, when we collide protons together, what actually happens is the quarks and the gluons inside the protons, those are the things that actually hit head on, and we can create things like Higgs bosons. For example, if you smush two gluons together, really high energy head on, one gluon from each proton, that's the easiest way to make a Higgs boson. When
So,
we take, oh yeah,
sorry, just I'm going to lose you in a second, but I wanted to mention a quick historical thing. We did collide electrons and positrons in the LHC tunnel several decades before. But anyway, back to you.
yes,
That was called
that
that
is true.
tunnel. Rather.
Yeah, before the LHC existed, as Andre said, we actually reused the tunnel. There was a different accelerator in the tunnel before called LEP, the Large Electron Positron Collider, and that was smashing electron positron, which is also a completely different type of physics that you can do when you're smashing electrons together. I'm going to talk a little bit more about the heavy ions though, because that's what we're getting ready for now. Heavy ion physics is really interesting. What happens when you smash lead ions? Lead, they've got 200 and something protons and neutrons in a lead ion. So when you smash these things together, what actually happens? You don't get these head-on collisions between the quarks and gluons necessary, but what you end up doing is you get something that we call quark-gluon plasma, which is like the super fluid made up of quarks and gluons that kind of makes this big globule of the superfluid. And that is actually what the universe looked like fraction of a second after the Big Bang. So by doing this, we're able to study literally like how the universe was at very early moments of its existence.
So, Claire, can I jump in very quickly?
Yes,
So
please.
we're now 97 meters on the ground, and we're about to go through a second material access device. So this time you can see the color is different, and that's because this is part of the safety system at the LHC. So going through this device requires quite a lot of conditions to be met. So as you can see right now, we are in restricted mode, and that means that we have access to the experimental area, but that is because we're in a technical stop right now. So there's no collisions happening at the moment. There's no beams that are circulating around the LHC. But then in this particular restricted mode, we actually access the areas with our personal dosimeter. But in addition to this, we have a key that I'm holding here. And this key is part of the interlock system. So it means that I get this key when I enter the experimental areas, and while this key is missing, it means that the LHC cannot work. So it's prevented from injecting any protons in the LHC, and the LHC will not work until I return this key to its place. So we're gonna go ahead and go in. I will just turn the key, sorry, into batch first, and then it will expect the key here, and then I can access the underground areas.
And we're going to remember when we come out to put the key back and not go home with it, because then
Exactly.
the LHC won't be able to run.
All right, that worked.
Yay.
Okay, so I can also say a few things. So we're about to access the CMS detector, and we actually have to walk around one of the the structures underground. So there's a graphic that we can show you, and perhaps you can even point to the exact area where we are now. We have to kind of go around, and there's a wall that separates where we are at the moment from where the detector is. And this is a wall that's 7 meters thick. So we're gonna have to walk a few meters to get around this, and then we can enter the detector. And we will, as you will see, we will enter from the floor of the detector. We have another entrance that's sort of 2 stories, 2 or 3 stories above.
On the diagram on the screen, the label PM54, that is where the lift that Andres took goes. The cavern that holds the detector itself is this short fat sausage shaped thing that's got the label PX56. And Andres is walking.
We call it UXT55, Underground Experimental Cavern.
No, I know. I'm talking about the label. But Andres is now walking around that tunnel, and he's going to come in at the one end of the detector itself, and soon you are going to see how beautiful.
Let's hope they can get through.
Yes. Is it dangerous? So there are dangers because we have there's a high magnetic field in right now, which Andres will show you. There are cryogenic gases and liquids that are used to cool different parts of our detector and our magnets, as well as the beam itself, when running, produces some radiation. However, CERN works very, very hard to make sure that that all the dangers are minimized as much as possible. Part of that is requiring us as physicists to have really extensive training to allow us to go into these places. So Andres has to pass a bunch of tests just to be able to have the access rights to be able to go into this cavern.
I think we should explain why they are fiddling at this moment.
Yeah.
So in order,
of magnets.
Yeah, exactly. In order to avoid the viewers to get sick, we use a gimbal system for the camera. Well, unfortunately, this gimbal system is not compatible with our magnetic field. So now they are, yes, exactly, that's what they use. And now we are turning to the, you might see, the more shaky selfie stick.
You see, if we have this thing on a gimbal, and then we walk in a magnetic field, the magnetic field will essentially force the camera to be pointed in one direction.
It would tilt, and at some point it would give up.
So you will see very, very cool. In fact, our magnets, we have a magnet that runs a current of 18,000 amps through it to provide a magnetic field of almost 4 Tesla.
Yeah,
right,
and we can
the detector.
We will demonstrate it just shortly. But yeah, this is the door that we're about to go through to show you the CMS detector. So welcome.
Yay!
In the meantime, we got a question about the piercing.
Look, that's our big detector. So
I will go stand close to the detector so you get a sense of scale. But we're talking about a detector our detector is 15 meters tall. Whoop. And I can already feel the magnetic field trying to steal these magnetic objects that I brought with me, but I'll show you that in a minute.
That's a really good way that you said that, Andres. You talk about bringing magnetic objects with you. Somebody was asking about going in with piercings. Usually, piercings are stainless steel, in which case they would be not affected by the magnetic field too much. So yeah, but look at that that spanner, and
oh my God. It's actually really hard to get this thing off. So yeah, so you can, I'm sure, appreciate the strength of the magnetic field where we're standing right now. And now, keep in mind that the 4 Tesla that we talked about, it's 3.8 Tesla, but that's inside our magnet, which is a superconducting solenoid that is 6 meters in inner diameter and close to 10 meters long, or I think it might be a bit longer. Anyway, around 10 meters long. But inside the magnet, we generate that very strong magnetic field. Outside of the magnet, in this type of magnet that we call a solenoid, the magnetic field line would sort of dissipate very quickly. So we have a lot of steel that surrounds our magnet. And when I say a lot of steel, all of these red objects that you see around, that is steel. And in total, we have about 12,500 tons of steel in our detector. So that's most of the weight of the entire thing, right? The entire CMS detector is about 14,000 tons. And of those, about 12,500 are steel. And the reason for all that steel is to reinforce the magnetic field outside of the magnet. So inside the magnet, we have 3.8 Tesla. Outside of the magnet, we have about 2 Tesla. And here where we're standing, it's a bit less, but still a very significant magnetic field.
What you feel at the edge is something like half a Tesla, and this is far the strongest in the cavern. Where you are standing, it decays, as you just said, it decays very rapidly. So your body feels a very small, not half a Tesla.
Every time I see Andres in there, he's got like more and more things. So he's got like 3 things now hanging.
We have a kit.
That's the effect of the magnetic field on our guides, I'm afraid.
So,
we must make you a Dr. Octopus suit or something. You can go in there with like all your legs.
So we've had this companion with us a few times when we go in and the magnet is on. So I decided with Claire, we're going to call it Mr. Quack. And we have just a paper clip just attached to it. And it will just go crazy under the magnetic field. I can just let it go. And you can see that it basically flies. You can see it. It's like standing up on my hand. So it's a lot of fun to play around with this guy.
Ooh. Oh, that was cool.
Yeah, so it also sometimes you can get it to spin quite a lot.
That's awesome.
So you can do a lot of tricks with this guy.
Dancing ducks in our detector.
Yeah, so we shouldn't spend too long. That's the danger of this is you have so much fun playing with the magnet that we don't show you other things. So let's leave it here and come back for it. And we will walk around. If you have any specific things about the CMS detector you want to see,
don't leave these equipment inside the field, please.
Of course.
Yeah, we'll make sure we come back for those.
Actually, since we're here, maybe I can show very quickly these orange, we already kind of saw them, but these orange objects, these are air pads. And we basically use these to move the CMS slices around. So CMS was designed and built in a modular way, which means that CMS, overall, it looks like a very big cylinder. You can think of it as cylinders inside of, or let's say barrels inside of barrels inside of barrels. But each of these, or we say almost like a cylindrical onion, and you can imagine a cylindrical onion that you chop into, I don't know, about a dozen slices. And the thing with CMS is that these slices are very heavy, as you might imagine, but we can still move them. You can see that there's several of these air pads. And so what we do is we blow compressed air through these air pads, and they act a little bit like a hovercraft, and then we can very slowly, we can move them. You can see that there are these guides, these anchors that we use. And there's a winch system at the end here. This blue winch system is what we use to move the slices. And we do that when there's a period of maintenance. We can open up CMS and access the inside of the different areas of the detector. And so this is exactly what we will do at the end of the run. So this will happen at the end of June, basically. So okay, we'll walk around a bit, and yeah, Claire, go ahead if there's any questions.
Sure, I want to show this little cute 3D printed rainbow detector. As you can see, it's not really rainbow colored in real life, but just to show you what Andres was talking about the layers and the slices. So our detector is as you said, it's shaped like a bit of kind of a cylinder or a barrel, and then with a lid that goes on each end. And the detector itself it's split up into 15 different slices. And using those pads, we're able to move these slices apart. Obviously, it takes a while, but we can do that and then access the inner bits of the detector to do some work on it, or replace things or whatever. So yeah, that's just gives you a bit of a context about what you're seeing. And right now, because we have a short stop, we're not actually opening any of these slices at all. So what you're seeing over there is right at the end of the detector, and then the beam obviously goes through the middle. do beams always travel through the detector? Derek asks. No, not always, as right now they're not. However, the beam pipe does go through the detector and will always go through the detector. In other words, when the LHC is running with protons or lead or whatever else we may put in it, the thing has to travel through the center of the detector, whether or not we're actually taking data.
So I can maybe jump in and mention something rather quickly. So you can see this part of the detector that has this yellow supports, and this is called what we call the hadronic forward. So this process of opening up the detector, you can see that right on top of these supports, there's we can even see it a bit better from the side. Just I can quickly show you. So this is what we call the hadronic forward system. So this we can see it surrounded by the green scaffolding. And so when we open up the detector, we have to remove these orange blocks. These are what you can really see right now is the new forward shielding, but underneath those blocks, there's more shielding, and that we can open up. And the point is that once we are able to do that, we can lower the HF platform, and then that hadronic forward platform will go in here. You see this yellow doors. Inside, we have a garage. So we call this the HF garage. And this is where we keep the hadronic forward subsystem while we're opening up CMS. Okay, back to you, Claire.
Yeah, it's like a gigantic Tetris game. If you want to get into the middle bits of the detector, you have to move things around, and like those puzzles where you have to move the blocks around to get the other blocks into other places. Oh, one other thing that is really interesting about moving things is that the Large Hadron Collider ring is actually tilted at a few degrees. So we have the Jura Mountains on the one side, we have Lake Geneva on the other side, and the LHC is actually tilted a little bit because of the way the ground slopes. Now, when we build our detector to get the most precise measurements, we need to have our detector perfectly aligned with the LHC beam. So if the LHC beam is tilted a little bit, our detector as well is tilted at a few degree angle. Now it's very difficult to see, but you can imagine moving these slices, which weigh, I think the heaviest slice weighs 2,000 tons, moving these slices while you're trying to pull them on these pockets of air, and you're actually either pulling them up slightly uphill or slightly downhill, depending on which side you are. It's quite a technical and logistical effort that goes on there. So, we do physics, but we also do like engineering and logistics and all sorts of things. It requires all of these things to build a detector like this. Speaking
so
of
we're
beam
gonna
pipes,
walk. Yeah, so we're gonna walk around a bit more. So I just wanted to show you here. We have the platform here to access the hadronic forward. We can't do that right now, but this is access to the hadronic forward platform, and you can maybe see a lot of the infrastructure there. So that's one of the things we'll try to highlight is that it's not just this detector, right? But there's all sorts of infrastructure required. That means high voltage and low voltage, but it also means there are certain gases. We talked about cryogenics for the magnet, for example, but different parts of the detector required some mixture of gases, especially the muon systems. And then some parts of the detector need to run a very specific temperature. So there's cooling required for some of these systems. They all run at different temperatures, and they're all very close together. So that means that within, let's say, as you travel from the center of the detector outwards, you'll see dramatic changes in temperature with detectors that are very close to each other. So keeping them insulated from each other is part of the engineering challenge. This right here, this is just to give you an idea. You see these modules here, and if you look at the very top, you can see that it says UCLA. So that's the University of California, Los Angeles. And so that's because the group at UCLA was responsible for designing, and they're responsible for maintaining and operating these systems. And this is, I think, specific to the RPCs or CSCs. In fact, we have some CSC colleagues that are doing work in the cavern, so it's possible we run into them. And they're doing work right now, so we can chat about this a bit later. Okay, Claire, back to you.
So there's a very interesting question that's come through on YouTube that asks, how many particles have been detected until now? So I would like to know from you guys who are watching, what do you think that number is? And then we'll try and work it out for you. But go ahead and write down there in the chat on YouTube. I want to know. Let's see who gets closest to the actual number. Okay, I
So
don't actually know.
I wanted to show this really quickly. So we're sort of crawling inside the detector, and you can see hopefully that just above there's the orange. Yeah, that's okay. You should be able to see that where it says super layer here. And that's one of the actual modules that we use to measure muons. So these, I suspect, are DTs.
Yes.
Yeah, so these are muon systems that we refer to as drift tubes. We have several technologies that we use for muon measurement. So this is just one of multiple different detector types of detectors that we use to measure muons. Yeah, so Noemi just pointed out that you can also see the ENFN logo. So that's the Italian, let's say, university system, and we collaborate with them very closely on many parts of the detector. Since we're here, we can also show you guys just to our left. There's this gas tank that I'm not really familiar with, but you can find all sorts of interesting. Yeah, so it's for RPC. But I couldn't tell you much more. I'm not sure what it's for.
RPCs are muon detectors. We have 4 different types of detectors just to detect one type of particle called a muon.
RPCs are very fast.
Yes.
Yeah, RPC stands for resistive plate chambers. And yeah, these are also fast detectors. So we also use it for what we call the triggering system. So basically to select the more interesting interactions that we want to actually record. I see some infrastructure for, this is cooling for GEMS.
That's me.
And
Yay,
that's
GEMS.
yet another muon system. So that's the gas electron multipliers. And that's a new technology. So that's actually, for now, we have, let's say, prototypes that are in the detector, but we are expanding this system and we are using it for the upgrade as well.
Awesome.
But these are, well, they're beyond prototypes, right? They have been participating in the data taking now for a few years.
P11, what you see now, is well beyond being a prototype. This is a real detector.
Yeah.
Yeah.
And what you see is the water cooling of the detector. Obviously, all the sub-detectors use electronics to read out their signals, and this electronics might consume quite of an energy. Large part of it, this energy is dissipated through the electronics, just like on your TV set at home. And obviously, in this tight detector, as you might see, we have to actively cooling these electronics. That's the part that you have just seen. You might imagine that these earthbound problems are also in this detector, not just the particle detection. That is, by the way, very, very cool.
So maybe just as an interesting point in terms of orientation, let's say, we're now in the minus Z or minus Z side of the detector. So one way to think about this is this direction points towards the Alps. And then this direction points towards the Jura Mountains, which are very close by. But yeah, when you spend enough time down here in the detector, you get a sense of orientation, but it's very symmetric. So at first, it may not be obvious exactly where you are. So every now and then you see in the walls something that might, with spray paint, say, plus side or minus
Andres,
side.
that is something very characteristic on the negative end. Just look up.
Yeah,
Yes.
So we're going to look up here. And the first thing you see is that we have a crane just above us. This yellow structure is a crane. Now, keep in mind, as Claire was saying, some of these slices are hundreds of tons. And so these cranes cannot lift the slices themselves. We can move them, right? We use the winch system for that. But for these cranes, we cannot really lift the entire slice. We use this for lifting, for example, the orange shielding, the new forward shielding. So this we can move with the cranes. But anyways, I think what we're trying to highlight is that just beyond this, we might have to maneuver a little bit so you can see it better. We basically have the main shaft where we have basically a 15-meter diameter main shaft, and this was dug out precisely to allow the lowering of each of the CMS slices. But this process happened 2007, 2008. So this is when the detector was actually lowered down, and it's been down here since. But we still, of course, have the main shaft. We sometimes still use it to crane down smaller. I think the new forward shielding, we use the main shaft to lower it. And when we need to access the detector, it needs to be craned up all the way to the surface. So this is a nice view. We can maybe stand over here and show you guys the direction. So this is the center of the detector. And you can see that this is the path of the protons or whatever type of particle we're colliding. They will go straight down this direction, which we call the Z axis. And we don't see the beam pipe, right? This entire yellow, the shielding is wrapped around the beam pipe. And you would only see it when we're accessing the detector for maintenance or upgrades. So that will be the case in a few months. But for now, you don't see the beam pipe directly. What else can we show? Claire, is there anything else you want to point out?
So maybe somebody, Monique, has asked, what does this place sound like when the collider is fully running? And I think it doesn't really sound much different apart from the lack of human.
Yeah, I guess I would say, I mean, right now, what you don't hear this because there's, let's say, aggressive noise canceling on this microphone. But what I hear right now, it sounds mostly like fans or pumps. So kind of industrial sounding, if you will.
Yeah, there's like a bit of a hum, I guess, which is mostly, as you say, the ventilation. And
Those
stuff.
blue stuff you might see on the picture. These are the racks where we have electronics that are not on the detector themselves. And again, they need cooling. Just to recap what I told, they need cooling, and the cooling equipment's noise, what you usually hear. But this makes a very nice ambience of this cavern. Whenever I need to go down without this noise, I always get annoyed.
It's like eerily quiet.
Yeah.
So
I
wanted to show you guys.
Does not, the LHC beam itself does not make any sound at all. Mostly because the protons are traveling in a vacuum. So
I wanted to show you guys very quickly.
And also there is when the particles collide with each other or change their identity, they don't make a sound wave.
Yeah.
So it's very silent.
Maybe I can jump in very quickly. So you can see that we have a lot of these cables, and they're what we call the chain. This chain here, cable chain. So the purpose of this is that, as I said, when we move the CMS slices, one thing we absolutely do not want to do is to have to disconnect thousands of cables. So this system allows us to move these slices, displace them without having to disconnect. You can imagine that this chain will sort of bend and unfold to allow the cables to move.
Yeah.
So we're gonna go up.
Just for the numbers. Sorry, we have 120 million channels, and each requires power. Each requires to be read out. Many requires gases, cooling, again, whatever infrastructure. So you might imagine that our infrastructure is one of the most complex that has ever been built by the human race.
So imagine an onion, and now an onion that is sort of spherical shaped, and you've sliced the onion up into slices, and the onion has 120,000 little bits that need to be connected, and you have to be able to connect up all of those layers with all of those channels, with all of those slices, and still be able to move the slices apart without breaking anything. That's what it's like
It
to
is
build
not
a
just a
detector.
sculpture.
Yeah, so maybe I can jump in very quickly. I wanted to show you guys the view from where we are right now. And so you can see much better the main shaft. You can also actually see this red structure just above us. And this is an interesting part of the fire suppression system at CMS. There's multiple levels of fire suppression. These boxes are one of the sort of last resorts when all of the 5 other layers of protection are not enough. Then these will emit foam that will extinguish the fire. So this is in case that our detector is actually on fire. And as I said, it's sort of a last resort because it will very likely damage the detector, but the fire will absolutely do more damage than any foam. But anyway, it's part of the fire suppression system. And so if you look down, you can see this is my favorite view of CMS, so just from above. So we're at the uppermost level. So we're several stories up from the ground, and you can see down below into our detector. And in fact, when the detectors opened up, it's even a more dramatic view. So right now we're essentially ready for collisions. We'll be getting beam tomorrow already. So there's going to be beam commissioning activities. So there's going to be beam circulating. So there's no time. It's a month, at least a month long process to actually take all the steps to open up the detector. So we're not doing that now. But of course, after, as I said, the end of June, you will, I'm sure we will have an opportunity to do these kind of open visits, and you should be able to see how dramatic CMS looks when it's opened up. So we want to send you guys to the up and on top of the detector. So we're going to be crawling around and showing you guys what it looks like when you're standing on top of the detector, which is very exciting. Not something that you would normally see in a visit whatsoever. So this is sort of a special opportunity, a special treat for you guys. And just as a quick note, we have this the helium reservoir that holds a lot of helium. This is part of the system for our magnet. So, and we'll go around, and Claire and Zoltan, you're welcome to add a bit more detail as we walk around.
Yeah, it's
5
liquid,
cubic meters.
5 cubic meters,
Yeah.
and it's liquid helium, which is, and it's at it's at 5 Kelvin, right?
4.2. But what is important that we just soak the superconductive magnet with liquid helium. From this reservoir, we constantly pour down the helium on the solenoid. If we would have time at the end, they could show Andres and Noemi could show the other end of this system, the helium liquefier. We use the helium in a closed system. Obviously, we don't make parties out of the helium. We don't waste it. The helium happens to be more and more expensive on the market. We cannot afford to just to release it in the air.
Right. Yeah, so the magnet obviously is a superconducting magnet, and so being a we have to have it cooled down to the 4.2 Kelvin of the liquid helium. Otherwise, the thing would just melt. You can't put 18,000 amps through anything if it's not superconducting.
You can.
Well, you can,
but you need to cool it again.
You're left with a very unpleasant blob afterwards.
Well, it would be very much suboptimal, I would say, to cool such a copper magnet, and also that would be much bigger.
Yeah.
That would be very inconvenient. Instead, what we are using is few square millimeters where we pass through this 18,640 amps. Itself, it is really much amazing as well, but also the technology behind how you make a superconductive magnet out of.
So maybe I can quickly show you guys. I mean, I'm trying to peek inside the detector, and I can maybe show you guys. If you look, there's a label down there that says RE. So that's the art. I don't know if you can see it. I'm sorry. I'm trying to just shine some light on it.
Where is it? We see the orange and
Where
we
the
see
yellow
the
is.
stripe. Yeah.
Where the yellow is.
Yeah, you
Oh,
see a
there,
label
the
there,
white label.
RE.
Yeah.
Yeah,
RE
so that's
something.
the part of the RPCN cap. But then just closer to us on the right, this structure here, these are part of the cathode strip chamber. So these are some of the actual, you can see this label here says ME. And this is one of the cathode strip chamber modules. So part of what I was trying to display here is that our detector is very dense, right? So everything is very close together. You can see there's, again, lots of cables, lots of infrastructure. So there's a lot going on in a very small amount of space. I mean, this detector, I'm sure, it looks really large. But when you consider everything that's inside and how heavy it is and how many systems are in here and all the cables that it requires and so on, it's really remarkable how dense it is.
Yeah, and the CSCs, the cathode strip chambers, as you mentioned, the team of people working on them, they're inserting something interesting now, right?
Yes, so they're actually, as we speak, they should be installing what they call demonstrator boards, and these are I think closer to prototypes for what they will the upgrades that they will be carrying out for the high luminosity upgrade. And the idea is that they can install them now, and then if everything goes well, they can take data for the heavy ion during the heavy ion period, and then they can use that to inform any adjustments that need to be made for the in anticipation of the high luminosity upgrade. So if we're lucky, we might see some of them around the cavern, but probably not where we are, because we're right on top of the detector.
Yeah. Yeah, it's amazing.
So,
I mean, if you think about it, we
yeah.
built this detector in 2007. Well, it was built before, installed 2007, 2008. The detector's been running for, since then until now. We're going to shut down and then for a couple of years and then run again until 2040. And we're still creating new bits of detector. And in fact, in June, at the end of June, we're gonna rip out the entire central part of this detector and get ready to replace it with a brand new tracker. So the work never stops, even though we've been going for a while. There's still a lot more to do.
So as Claire said, this is an ever-changing equipment. This is not just something that we built up once once a time and then.
So if I can
got
jump
a
in
very interesting question.
We did. We got a lovely question from Monique asking us if the detector could tell us one secret tomorrow.
Only one.
What do we wish that could be? Only one. What's your favorite?
I have a favorite.
What's your favorite?
Well,
this is Zoltan, by the way. He's hiding.
I'm somewhere here. Not just because I don't like the camera. Indeed, I like.
What's your favorite? What's your favorite?
Favorite.
Yeah.
My favorite thing is the dark matter.
Yes. Yeah. That would, that if it could just give us a hint of dark matter, I think I'm with you there. That would be really cool.
This is one of the most intriguing questions.
Yeah, it really is. I mean, it makes up
among the other
25% of the universe, and we have no idea what it is.
Exactly.
So,
Andres, what about you? What would you like? What secret would you like to know?
Yeah, I mean, dark matter is, I think, the most. Yeah, let's put it this way: it would be the most interesting direct thing that we can potentially observe at the LHC. But there's all sorts of possibilities, and for me, the most interesting would be something so completely unexpected, something that nobody has thought of before. That would be the most interesting to me, because so far the standard model has been very successful, too successful, suspiciously successful.
Yeah, exactly.
Like we know there are more things out there, right? So we have an incomplete understanding, and this is we can think about it this way: our job as researchers is to try to break the standard model. I mean, we are challenging the standard model all the time. And we as physicists, in addition, not just experimental particle physicists, but also theorists, try to come up with ways that, maybe this possibility, maybe nature could behave in this way. And then we try to test it. But I think to answer the question, I think something completely unexpected would be the most interesting.
Yeah, just for so the standard model that Andres is talking about, that is the best model or that we have of how the universe works and why it works and looks the way it does. But it's annoying because the standard model does not tell us what dark matter is. We know that dark matter exists because of measurements that we've done in space. We know it. We know dark matter exists. We just have no idea what it is. The standard model gives us no clues. Theorists have come up with thousands of possibilities of what it could be, and our job as experimentalists is to make measurements of things that the universe does, and then the theorists can compare their proposed theories to the results that we get. And right now, because we haven't, what Andres is saying is it would be so cool if we could measure something and find something completely unexpected, something that even the theorists hadn't even thought of.
I think
yet.
that would be the real cherry
cool.
on the cake. But as Claire said, the standard model, as we used to say, is incomplete.
Yeah.
That's a sad thing.
And who knows? Maybe one of you guys watching will actually end up coming up with the reason and the discovery of dark matter. Andres is collecting his bits and pieces.
Oh yeah.
Yeah. So
yeah.
I was going to say,
anything in.
Of course. So we are more or less, we want to keep this to around 1 hour. So we should say goodbye to the detector, and there's other things we want to show you on the other side of this wall, and then on the surface. But yeah, this here as an example, this is interesting. This looks like a door, but it's actually a concrete block that is 7 meters thick, right? So this wall that I'm sort of in between now, that goes along something like 30 meters, and then this block is actually 7 meters, and we can move this out of the way when we have an access, and this will allow us to get into the elevator shaft, which is just on the other side. So we're gonna go back to the elevator.
Okay, if you guys come to CMS for a visit, the pathway that we will take you underground actually goes on the other side of that door that Andres is showing.
If this plug is open, they can
even sometimes see inside.
That's very spectacular.
Yeah. So we found some CSC colleagues.
Ah, there we go. Yay.
Yeah.
Wave. Yay.
So as we already mentioned, we are in the so-called technical stop. This is a 2 days period when we don't have beam in the machine, we don't have beam in the accelerator. We have the opportunity to go in the detector to repair things, tweak things, or configure things. This is a very rare occasion. This didn't happen this year before.
Yeah, this is the first one.
This is the first time. Yeah. This year, obviously, by time to time, almost every week, we can have an access. We can make a fast repair if needed, if an electronics board needs to be replaced, that we can do. This is a little bit longer now. And apart from these periods, we have the so-called year-end technical stops, a few months every year at the end of the year, except the Christmas break, because then we are all sent home to our families. But then we can do a little bit more, and also the long shutdowns that is at this moment is just thematizes our life. These are those year-long or several year-long periods when we do really the upgrade to the detectors. We already have a very long list at CMS what we are going to change during the next
or in a bit
2, 3, 4 years. Obviously, we want to make it very quick.
Yeah.
Because we have to go back to the data taking. We really want to see if there is something unexpected.
We got a quick little view there of Noemi, our camera person. Thank you, Noemi. Andres, grab the camera.
So we're saying thanks to you. Yeah.
I think they're switching back to the gimbal. The proper gimbal. Speaking of that, which relates to the magnetic field, somebody was asking, why do we keep the magnetic field active even while the collider is not running and while we're not taking data? The fact is, it's actually quite brutal to do a magnet cycle. So this is a superconducting magnet. The magnet itself is oh, we lost this. Ah, there we go. So the magnet itself is made up of a niobium titanium coil, and we pump 18,000 amps through this. Now that is a lot of current, and what happens is, your metal structure gets, aligned and produces this magnetic field. But turning it off and on is a huge big procedure. You can imagine ramping down 18,000 amps is not an easy task. It takes something like 6 hours, I think, even to just ramp
like
down.
that. But also, if you change these forces are meganewtons on the support structure. That changing these forces would lead to a fatigue, mechanical fatigue.
Yeah.
And actually, the mechanical fatigue that limits the lifetime of our detector.
Right.
The magnet.
We only have like you have a finite number of times that you can turn the magnet off and on. So, things do happen. We had a power cut here a couple of weeks ago, and as a result, the magnet got ramped down accidentally. These are things that you have to take into account when you're building something like this, because this magnet, we've already had it for 16 years running, and it has to last until 2040.
And we don't have any spare part of
Yeah,
this.
we don't have another spare
only,
magnet. Like, we have this one. This is the only one.
So actually,
So we need to look after it.
what could really damage the support structure is as we call it, fast discharge. When we suddenly have to release the energy inside the magnet, when we have to pump it out, this is usually due to quenches. The magnet is designed such a way that it should minimize the probability of the quenches, but as the mechanical fatigue builds up, the probability grows, and when it reaches a certain point, it is no more feasible to operate the magnet anymore.
Yeah.
This is what we want to
since
push
we
back
are
as much as we can in time.
So since we're discussing the magnet, we are now in the elevator shaft, and we can show you some of the infrastructure that's related to the magnet. And specifically, we talked about the fast discharge. It doesn't matter if it's a fast or slow discharge. The point is, these 18,000 amperes of current, when we circulate all that current, it flows through these copper bars. And these copper bars, we call this the bus bar. You can see it on the left. And they have water circulating inside of them, because otherwise they would melt. And so this is the system that we use to basically ramp our magnet, to inject the current into it. We can show you guys very quickly the infrastructure for the magnet, and that's just ahead of us. And then we will go to the surface and hopefully show you a bit of HGCal. I think we will skip the service cavern in the interest of time.
Yeah.
Andres, while you are walking, let me just tell that the energy that we store in the magnet is somewhere around 2 gigajoules.
Yeah.
This is the kinetic energy of a wide-body aircraft.
Right, which is currently a record. So it's between 2 and 3 gigajoules, and that's the most energy stored of any magnet on Earth, and we hold that record, at least for now.
And we just don't want to let it go in one moment.
Yeah,
it's fly out in the air.
Yeah, it's brutal.
Yeah, so it is rather loud in here, so I can't hear you guys very well. But if you want to say a word about the cryo systems, please go ahead.
Well,
so that's the helium liquefier that we already mentioned. That we use the helium in a closed system. We never let it out in the air unless there is a real malfunctioning that we want to avoid, and we do everything against it. But in a normal case, the hot helium gas, we are talking about 20 kelvins,
as opposed to 4.
that's hot, because that's already boiled. That is brought back to this equipment, this liquefier equipment, where we cool it down again into a liquid phase and pump it back to the 5 cubic meter reservoir that you just seen inside. This is an industrial device. We didn't design it ourselves. We just ordered it from the stock. Oh yes, exactly. My
Leak
favorite
detector.
Desodor. Yeah.
The most high-tech thing that you will see today. Our leak detector. It's a soap
Don't
bubble.
forget that all these things have to be leak tight.
Yeah, sure.
If you have a leak, you have a loss of a gas or even liquid. Not just on the helium, mainly not on the helium, but on the pressurized air equipment. Obviously, you don't want it. You don't want to waste anything. Therefore, you always have to be very, very, very sure that the plumbing is done correctly. Again, some earthbound. I do quite a few plumbing in the gem detector.
Yeah. Yeah, you crawl around in amongst pipes and things.
Yeah, one of
pretty
the plumbers
fun.
there.
It's like exactly like Super Mario, crawling around in the pipe.
At least I'm still, yeah.
While Andres is in the lift, I'm going to go back to that question about the number of particles that are flying through our detector. And honestly, I think that it's just uncountable. If you want to know how many, so let's kind of work backwards, right? So when we have some protons colliding, they smash together, and you get a bunch of new particles that are created that fly outwards through our detector. And this is a diagram of an event that happened in 2016, where we had protons smashing together and a bunch of stuff flying outwards from that collision.
So,
okay.
Claire, maybe I can ask you, how many protons are we talking about when you say these protons come in and collide?
All right. So I was going to get there. So this picture that I'm showing you here shows one proton hitting one proton. But we don't fill up the LHC with just one proton at a time. We fill up the LHC with bunches of protons.
That comes from the technology of the accelerator.
Yes. It's very sophisticated to keep protons together in bunches because, as you can imagine, they're all positively charged, so they try to get away from each other. So you need good, electromagnetic fields and things to keep the bunches nice and bunched up. Now, in one bunch, we have 100 million protons, and we fill up the LHC with 2,400 bunches all the way around, right? When these bunches cross over, we don't just get one proton from each bunch hitting each other. We get, actually right now we're getting something like 65 protons. I think this is a picture of 20 odd collisions. So now we're talking about in one event, we're getting 65 of these vertices happening, with hundreds of tracks, sometimes hundreds of particles coming out from each one. Okay, so we're already talking about thousands of particles now happening every 25 nanoseconds. How much have we done so far? Well, we have collected a number, I don't know if you can see it in the control room, 323 inverse femtobarn.
Oh yeah, but this is what we collected since LS2
Yes.
shutdown.
Yeah, so only since 2022, right?
Mhm.
Yeah, so only in the last couple of years, we've collected 323 units
That's
of
a word
measurement.
record.
It's exactly.
That's a word record.
Now, what does that mean? Because that's a weird number. So one inverse femtobarn corresponds to about 100 trillion proton-proton collisions. So 323 of them, so 323 times 100, that's 32,000. Let's say 32,300, 32,000 trillion proton-proton collisions.
1 trillion is 10 to the 12.
10 to the 12, yeah.
And we are talking about 10 to the 15.
Yeah, 10 to what
You said
I'm sure-
3,000 trillion?
32,000.
32,000.
32,000.
3.2 10 to the 16.
Yeah. What's a 10 to the 15? I can't. It's a peta. That's peta, right?
These numbers are
I don't know.
too big for me.
Petillion.
I have a PhD in physics, but these numbers are
Let's go with 32,000 trillion proton-proton collisions, and each one gives you hundreds, if not thousands, of particles being, so it's a very, very big number.
Actually, it is very hard to collide protons. That's why we throw
100 billion of them at a time, and we only get 65.
Exactly. So you might imagine the proton is very small. And also, in addition, even if the protons collide, they disintegrate, they fly apart. But in most of the cases, nothing else happens.
Exactly.
As we call it, elastic scattering. That's a pool game, sorry. But when the material doesn't change to energy and back to material, only the material collides, just like the balls of the pool game. What we are interested in is the deeply inelastic.
Yes, where they actually smoosh together and create something new, like a Higgs boson,
Exactly.
hopefully dark
Something
matter.
that was not in the proton.
But you made a good point, because you said it's really, really hard to smash protons together. And the main thing that is happening in the next 4 years, the LHC is going to be upgrading their magnets to be able to squeeze these bunches of protons down even closer together. So when we start up again in 2029, 2030, instead of 65 protons hitting each other every 25 nanoseconds, we are going to be getting 200 protons hitting each other. So imagine this picture with all the vertices.
Completely yellow.
But yeah, times 10, all layered on top of each other. Yeah. We're going to get 200 of these vertices every 25 nanoseconds. And our current detector, many parts of it is just not up to that task. Yeah. And what Andres is about to show you is the new one that we're building.
One last word. Why do we do all of these? It's not just because we can make it. Of course, we are very clever. But the reason is why we have to do this, all those physics processes like the Higgs creation, and even more the dark matter and the exotic physics that we are talking. They are very rare. I know one number. If this day is about numbers already, I remember a number from a simulation of a Higgs creation of the with the setup that we had somewhere around in 2012 when we found the Higgs boson, and then we expected one Higgs boson created from every 3,000 billion proton-proton collisions.
Wow.
So you might imagine that what we are looking for is extremely rare.
Yeah.
That's the reason why we are throwing enormous number of protons on each other at an enormous frequency, and we are waiting for enormous long time to get the results.
Exactly.
Okay.
Andres is going to show us this very cool spaceship looking thing.
All right, maybe I can jump in here very quickly. Yeah, so I'm standing in front of one of two of the NCAP calorimeters for, again, the high luminosity LHC. And this is HGCal. You can see this structure behind me that looks a lot maybe like an Apollo capsule that landed on the moon. So this structure will house a very sophisticated next generation detector. And this will use a combination of technologies. So we're talking about silicon sensors. In fact, a large number of silicon sensors. And I think it might be a record number, but it's definitely more than the current tracker. And I think it's more than
like 2 billion channels in silicon after the long shutdown. By the way, this is a top edge detector. This is this is the most advanced that has ever been built.
Exactly. And so we also have a different type of calorimeter technology. It's more traditional. We call it a tile calorimeter. So I say that because traditionally we have used scintillators as calorimeters. That's not always the case. In Atlas, for example, they have the liquid argon calorimeter, but in CMS, at least, we typically use scintillators. This will be the first application, I would say, well, if you don't count the pre-shower. But anyways, it's going to be a large application of silicon sensors. And this entire structure, when it's fully completed, will weigh 250 tons. Yeah, you can see how Claire is demonstrating how it will fit in our detector. So it goes inside the magnet, really. And then what you can see now, right, you can see that there's definitely lots of cooling lines, and you can see that these are all connected. And so the activity that is on the table, right? So what the activity that we're going to be doing in the next week or two is to actually do a cold test. So this detector will operate at temperatures down to -35 to -40 degrees. And for that, we need a cooling system based on CO2, on carbon dioxide. And so what this test will entail is you can see there's temperature sensors all around in there at basically room temperature, but we will have to cool down this detector. And you can see there's a lot of
sophisticated one they have.
Yeah, so we have a lot of infrastructure here, and you can see that even inside of this box, inside of this container box, we have a chiller system, and you can see some of these lines are insulated already. So the chiller, as I just heard, is working now, but it's not circulating at the moment. But they are really getting ready for the cold test. Now, during this cold test, they will operate one of the cassettes, as they call it, and I don't know if this is the exact one that they're going to use, but I believe I saw what looked to me like some of the cassettes, but I'm not entirely sure. No, these are just part of the. So I don't know where they have the cassettes. The cassettes might be in the clean room, which is just on the road.
One question: why you mentioned that this is going to be cooled down very much? Why do we need to cool it down so much?
So the main reason is because when you're dealing with silicon sensors, I don't want to go into too much detail, but they basically acquire radiation damage. And so one of the ways to slow down that radiation damage is to keep them very cold. And then there's other more technical reasons, and there's a temperature dependence with what we call leakage current. That's I think maybe too technical, but I will also let Claire add anything to that if she knows a lot about this as well, so you can jump in and.
Yeah, you get so as Andres mentions, you get radiation damage just because that's part of being a particle detector. And then like a lot of the signals, like for example in our tracker, what we use a laser to cut. Well, we actually, our current tracker reads out an analog signal, it's converted into digital, and then you use a laser. And the cooler you make it, the stronger your laser signal gets. So actually what happened is we started off with the detector at I think -20 degrees, and as the years have progressed, we've lowered the tracking temperature. We're now sitting at -25, just because of the radiation damage as well.
Cool.
Yeah,
Really?
So it's,
maybe
but there's another question actually that somebody's asked, which is really interesting, and it's, do you have to worry about condensation when you're cooling these?
Maybe I can jump
Yes.
in very quickly because I wanted to mention all that. Right. So absolutely we do. So and not just that, I mentioned that this detector is going to be very, very close by to other detectors. So part of the test is making sure that this thing can be cooled down to -40 degrees, but all of the temperature and the conditions, you need to keep it very dry. That all is insulated, right? And part of what needs to be tested are what we call heating foils. So you can imagine this as just a very, very large freezer, a very large fridge, where you want it to be cold and dry inside, but not outside. At the same time, we can't afford the luxury of having a lot of insulation. We need to reduce the material as much as possible. So what we actually have are heating foils, heating pads, let's say, that heat just the outside surface, so that that's the fastest way to insulate it, if you will. And so that applies to other detectors as well. I wanted to show you the application in HDCal since it's very relevant to what we're seeing right now. But the same applies to other detectors like the tracking detector
Yeah, I
It
mean,
does need to be kept dry, and there's an entire system that needs to be runs unattended, that keeps track of the temperatures and takes action in case that the supply of dry air is interrupted or there's an interruption in the cooling. So there's a sequence of actions that need to take place without any human intervention at all times. Needs to be super robust,
and we
which also
measure the
Claire
dew
knows a lot
points.
about.
We measure the dew points. We have like multiple sensors all the way around on the inside of the detector measuring the dew points. And if the dew point temperature gets close to the temperature of the tracker, or the tracking temperature raises, too warm and gets too close to the dew point, then protection mechanisms set in to turn off the voltages and everything to protect the detector. There's a lot of more of the parts of the detector are actually sensors and readout and things that it's not actually detecting. So just protection.
We are
for
talking about one of or probably the most complex device that has ever been built.
Yeah.
We are not the only one. The Atlas and LHCb and Alice are the other ones. But what is
I think it's so fascinating, but nobody knows the entirety
this leads us
of
to the next question.
exactly.
Indeed,
Yeah.
I wanted to go there as well. So there was a question whether there is anyone who understands all the aspects of the detector. I would say no, it's impossible. However, we know our own little field, probably as much as we can, and we put together all this information. If we know that there is something that we don't understand or we don't know, especially at the interfaces, then we immediately look out for the colleagues and we ask them.
Look, they're outside in the sun. Yeah, I mean, even people who were here from the beginning, who built the detector, built parts of the detector. I think, like all of these sciences, right? You can know a general amount about everything, but like if you really want to know like the deep specific stuff to solve problems and debug or design things or whatever, those very deep focuses, it's just, I don't think there's enough time in your lifetime to learn about, but
Indeed,
it is fun to try. Exactly.
That's very funny. People love to learn.
Yeah. It keeps it interesting, right? Like every single day you learn something new.
Exactly.
Yeah.
Yeah.
Even during this discussion, I learned quite a few.
Yes, same.
Thank you. Sorry, Andres. Oh yeah, we lost him.
Oh, we lost. Oh no, he's back. Are you back? I think
I don't know if you can hear me, but
yes.
Yeah.
Control room.
There we go. Oh look, you're going to be coming in. Maybe we'll see them coming in through the window there
soon.
Yeah. So but I think that's a good time to wrap up here, I think, because
let's wait for Andres.
No, absolutely. We'll make sure that he comes back in. But yeah, thank you so much. Oh,
yes,
there he is. Thank you so much to everybody who joined us today. It was really cool. We don't get an opportunity. We haven't had many opportunities to go into the cabin this year, so it was super fun. And thank you for the amazing questions.
Yeah, really nice questions. So thanks a lot.
Thank you for your amazing tour and with Mr. Cracky the Duck and all of your other bits and pieces. Thank you, Noemi, and thank you, Zoltan, for doing the technical and the camera work. And thanks again to all of you guys for joining us. Thank you to Rona and Nefeli behind the scenes who are passing on the questions. And obviously everybody in the control room who are doing their jobs and allowing us to sit here and talk to you.
Thank you so much. Have a nice day.
Have a great afternoon. Bye-bye.